Alrighty, here's 7-4, just a single day. Sum and difference formulas, right? Really, you can see there in the learning target, our objective. We will really stay focused on a couple things. Evaluating trig functions is going to be one of them. You'll see that on this slide. And really simplifying or evaluating expressions. It says to solve trig equations. You're not actually going to see any of that on here today. We're not going to do any solving. But yeah, we'll get started here on the first slide with getting some exact. That's our fill in the blank right here. Exact trig values other than the 16 on the unit circle. Okay, it's one of the things we can use the sum and difference formulas for. Now there's 6 of them, one sum and one difference for sine and cosine. You only apply one of them to any given problem. For example, cosine of 75, I go right to the 2 that are in terms of cosine. That's, it's got to be one of those 2 because I'm trying to get the exact cosine value of 75 degrees. And what you do is you look at what you have and you think to yourself, all right, I got to split this up in terms of 2 angles that are on the unit circle, okay? For most, there's a number of different ways you could do it, but for example, on this one, I think the way you would kind of be most likely to come up with yourself would be, let's rewrite 75 as 30 and 45, okay? Again, 2 things going on there. 30 plus 45 is 75, right? But, there's a lot of ways to split up and write a sum of 2 numbers that add up to 75. These 2 happen to be on the unit circle, okay? And that's a big thing. All right, really big thing. So now I'm using the cosine sum formula, which would be right here. Okay, and that would say cosine 30 times cosine 45, right? 'Cause basically the way I'm approaching this. That's U, that's V. Minus sine of 30. I got to drop down here times sine of 45. Wish I could have written that all out on one line like you see it, even though I kind of erased here, or not erased, but covered up. That you couldn't see that was sine of V, right? Because again, I'm saying wherever I see a U, I'm putting a 30. Wherever I see a V, that's 45, okay? Now, once it's in terms of all these angles that are in the unit circle, I can go to the unit circle and make all these substitutions. For example, cosine of 30 is the square root of 3 over 2. Cosine of 45 is square root 2 over 2. Minus sine of 30 is 1/2. Sine of 45 is square root 2 over 2. We continue to simplify and get that. Square root 6 minus square root 2 over 4, okay? Again, what we've kind of to jump to being able to do here is that is a cosine value, an exact one, right? Not a decimal approximation from our calculator. It's exact for an angle that's not on the unit circle, okay? That's the exact cosine value of 75 degrees, okay? Part B is in radians. That It can be done, but generally speaking, I would advise you that this is not a good idea to try to do it in radians. It's very possible. I could show you how to do it. You could figure it out. It's just kind of more work than is necessary, that if you're going to rewrite as a sum or a difference, you probably just want to switch over to degrees. It's a lot easier, okay? Again, in radians it can be done, but as far as how you're going to split the number up as a sum or difference, it's so much harder. To the point where I don't think it's worth taking the time to do that. Rather, I would take this approach and just say, okay, because it's the exact same question. We want the exact sine value of 15 degrees, okay? We're just going to call it, an angle in degrees as opposed to in radians. And again, you would find a lot of different ways you could do this. I'm going to go with 60 minus 45. Do keep in mind at that step, though, you have to break it down into two angles that are on the unit circle, okay? Now, you might have thought 45 and 30. That would work. 45 and 30 would work perfectly. I just happen to go 60 and 45. All right, so now I'm on the second row with the sine difference formula. There's U. There's V, okay? So it says sine of U which would be sine of 60 times cosine V minus cosine 60. I'm committed to getting this one all in on one line. Sine of 45. Sort of did, except my dash line kind of got in the way. Good enough. Okay. Sine 60 times cosine 45 minus cosine 60 times sine 45. And then we go through on the unit circle and make all of these substitutions right off of it. Need some more room to scroll down here. We actually end up getting the same answer, okay? Which we actually could have predicted because 75 and 15 both add up to 90, so they're complements. One's sine, one's cosine. We've actually seen that before. If you actually look back to your list of identities, a co-function identity tells us that would have happened, right? That cosine of 75 is the same as the sine value of 15, okay? Okay, let's take a peek here at tangent. 105, right? Again, first thing, how I want to split this up, I'll go 60 plus 45 to get the tangent value of 105. And you probably notice tangent looks a little bit different. It always does. Like every time we have like a new formula or a new way of looking at sine, cosine, tangent, tangent's always a little bit different. It's a different ratio that does not have the hypotenuse in its definition. So its properties play out a little bit differently. I'm using the tangent sum formula, which is right here, by the way. Okay. It's a big game of substituting, but this actually gets to be a little bit trickier unless you have these values on your unit circle, right? The tangent, because the unit circle says sine and cosine, but, so you can just read them. But tangent is y over x, right? So you'd have to divide y by x. I'm not going to show you the work for it because we've done it before, but tangent of 60 is the square root of 3. Tangent of 45 is 1. So we would end up with which would just be square root of 3 plus 1 over 1 minus square root of 3. Which, real quick, we should rationalize this. Taking us way back to functions, but we got that square root on the bottom. We want to multiply by the conjugate, okay? Multiply by the conjugate, which will leave us up top with square root 3. It's like the top and bottom are like both a FOIL. Plus 3 plus 1 plus square root 3, and then the bottom will be 1 plus square root 3 minus square root 3. Okay? Those are going to cancel, right? That's why we did the whole conjugate thing. The bottom becomes negative 2. And then the top becomes, let's see here, 4. We have like terms, 3 plus 1 plus 2 square root 3. Okay? We could actually take this one step further. If we factor out a negative 2 out of the top, we would have negative 2 minus square root 3. Those would cancel, and finally we arrive at our final answer, negative 2 minus square root 3. Okay? Keep in mind, value-wise, that's no different than what we had up here. Everything beyond there is just simplifying to get the square root out of the bottom. Okay? Most wouldn't have quite that much simplifying, but that one does. Okay? True or false? The sine of 120 plus 45 equals the sine of 120 plus the sine of 45. Well, let's apply the sine of 120 plus 45. The sine sum formula, which if you go back to your list of formulas here, 120 is u, 45 is v. It would say this. This is the sine of 120 times the cosine of 45 plus the cosine of 120 times the sine of 45. There's nothing to factor out. There is no way to simplify that, right? Here is sine of 120, which that has. Here is sine of 45, but you've got these other numbers with them that aren't 1, right? And we can't factor anything out, so no, that does not equal sine of 120 plus the sine of 45, right? Kind of a tempting jump to make because you're like, yeah, it should, right? If we were doing the sine value of those two angles added together, it should just be the sum of their sine values separately. But you look at the sine difference formula, and that is not the case. All right, here we're going to get another exact sine value, u plus v. Okay? Except it doesn't involve the unit circle. I got to draw a couple of diagrams. An angle u and angle v. I don't know the angle itself, but I know its sine value. I have a second angle where I know its cosine value. So here is angle u. It says that number one, it says right here, It's in quadrant 1, which means y is 4, r is 5. Oh, and then right here, it's another Pythagorean theorem. X is 3, right? You've seen that case. You wouldn't have to write out the work for the Pythagorean theorem. You've seen the 3, 4, 5 case many times, okay? So one other thing that I want from this diagram, the first is not it, because I already knew. Use sine value is 4/5. But I can see from here with x over r that its cosine value is 3/5, right? Because way down here, I'm looking ahead that I'm going to get the sine of u plus v. That's what I'm after here. That is the sine of u times cosine of v, which I don't have yet, plus, this is what I was thinking of, cosine u sine v. Okay, so I knew I was going to have to get the cosine value of u, okay? But now I've got it. It's 3/5. And in fact, if I were to try to simplify this right now, I'd say, hey, sine of u is 4/5. Cosine u is 3/5. Cosine of v is negative 12 over 13. And then here we need another diagram, this time for angle v, which it says right over here, right? It's between pi over 2 and pi, which tells me the angle's in quadrant number 2. Okay. I know this is negative 12. R is 13, right? That's x over r. Here I think you'd probably have to write out the Pythagorean theorem. We're missing y squared plus negative 12 squared is 13 squared. Solve that, you get that y is 5. Right, but that does what we need it to do, because now I can look at that and see y over r, that's my missing piece. Sine of v is 5 over 13. Here's a bunch of simplifying. Negative 48 over 65 plus 15 over 65. Adding fractions, but we already have a common denominator. Negative 33 over 65. Okay, and again, just to bring us back, because in all that procedural stuff, it's easy to lose sight of, like, what did we just do again? We found the exact sine value of those two angles added together if they were combined. Okay, I don't know exactly what their measurements are, but one is in one is in quadrant 1, the other's in 2. Okay, but if we combine them into one angle and added them, that would be its sine value. In one of our cofunction identities, we have seen this, that the cosine of pi over 2 minus x equals sine of x. With the cosine difference formula, which really fits the form of the left side, this is pretty easy to prove, okay? Cosine difference would state this is equal to cosine of pi over 2. That's an exact value we can get from the unit circle, times cosine of x plus sine of pi over 2 times sine of x. Now, if it helps, as I'm relating it to the formula, it's like pi over 2 is u, and it's like x is the v, okay? Unit circle tells me cosine of pi over 2 is 0. Sine of pi over 2 is 1. That part's gone because it's been multiplied by 0. Sine of x times 1 is just sine of x. Okay? Again, we've already seen that. We had it on our list of our identities back from, I think, the very first day of chapter 7. But there you go. With the cosine difference formula, not too bad to prove it. All right, a couple others that we're going to do here just to simplify and get these expressions only in terms of theta. Okay, only in terms of theta. All right, cosine difference formula right here, which is actually going to be the same formula that we used on the slide before, right? Cosine theta times cosine of 3 pi over 2 okay? Cosine of 3 pi over 2, that's unit circle stuff, that's 0. Sine of theta. Sine of 3 pi over 2 is -1. Very similar to the one before on that previous slide. We do get to a different, I should have a theta in there. A different answer though, throw that negative sign out front. That would simplify to negative sine theta, which fits what the direction said. It just wanted it in terms of theta. I don't care that the trig function changed. That's just kind of what the formula led me to. Okay, but notice right here, it is just in terms of theta. Okay, try the same thing with tangent. Tangent sum formula would say tangent of 3 pi plus tangent of theta over 1 minus tangent of 3 pi okay? Tangent of 3 pi, that's like a trip and a half around the unit circle. So it basically would kind of put you back at pi, which you could also figure out from a coterminal, right? We could always subtract or add 2 pi to get back to the same spot. So it's like you're looking at the unit circle, but you're at the point of pi. At that spot, you find tangent is 0. Top just becomes tangent of theta. Bottom is just 1. That whole thing could just be simplified to the tangent of theta. Okay? Those are your sum and difference formulas. Okay? That's a pretty fair amount on them. That was 5 slides worth, but a lot of simplifying on a lot of those problems. Hopefully you're seeing that a lot of times the application of the formula isn't terrible. You have some simplifying to do a lot of times after you've gotten everything plugged in. In 7.5, the only thing that's left coming your way for Chapter 7a, right, our first half of Chapter 7, is the double angle formulas, which is going to be pretty similar stuff. Different formulas, but kind of the same idea.